external interface in Lucene. Now we are focusing on external interface. Now we are focusing on Lucene searcher. org.apache.lucene.search provides data structures to represent queries. That is term query for individual words, phrase query for phrases, and Boolean query for Boolean combination of queries, and the index searcher which turns queries into top docs. A number of query parsers are provided for producing query structures from strings or XML. Here you can see Lucene searching mechanism. As shown in this figure, the query string requested by the user will be passed by the query parser class in the beginning. Not only just pass the string into the corresponding query object for searching, but also tokenize every word of the indexes using the particular analyzer that is the same as the one during the indexing process. Finally, search the build index. Finally, search the build index files for query results, which will be encapsulated in top docs class and return back to users. Here user is connected to query string. Query string is connected to query parser and analyzer, which has query parser and language analyzer. Query parser is connected to language analyzer. Query parser and analyzer is connected to index files. Index files are connected to return search results. Return search results are connected to documents, and documents are connected to show results to user, and show results to user is connected to user. Here you can see indexing and search. Apache Lucene is an open source Java-based indexing and search technology. It is a technology suitable for any application that requires full text search, especially cross-platform. Lucene works by first indexing the data to be searched, and then using index for searching. Indexing is the process of converting text data into a format that facilitates rapid searching. Lucene stores the data in the form of inverted index. An analogy is an index at the end of a book, and index points to the location of topics that appear in the book. There will be terms created from the input which point to the documents. Terms are indexed, and any search is performed on terms, and related documents are fetched. Lucene index is built over an implementation of the directory class. Lucene supports multiple directory implementation. RAM directory, complete index is kept in the memory. FS directory, complete index is stored in the file system. NIOFS directory supports multiple threads on FS directory. Terms to be created for indexing can be governed by something called analyzers. The analysis, the input to be indexed can be analyzed to extract the terms on which the searching can be done, like extracting word. removing common words and changing the words to lowercase, etc. Analyzers are used to, both at indexing time and searching time. It is highly recommended to use same analyzers both at index creation and searching time, so that tokens created for searching are created in the same way that the data is indexed. Analyzers internally use tokenizers and filters. Analyzers can take a string as input and returns back to the stream of tokens. Lucene provides some out-of-box analyzers which come handy. In addition to custom analysis can also be created. Some analyzers are simple analyzer, standard analyzer, white space analyzer, n-gram filters, n-gram token filter, h n-gram token filter, length filter. Adding data to an index. Lucene index comprises document which contain fields. Field represent a piece of data queried and retrieved in a search. Field class encapsulate the field name and its value. Lucene provides options to specify if a field needs to be indexed or analyzed, if its value needs to be stored. Field contains terms which are used for querying. Each field has semantics about how it is created and stored, that is tokenized, untokenized, raw data, compressed, etc. Document represents a collection of all fields. Term point to documents. The data that needs to be retrieved through searching needs to be stored in a form of document. Index writer, the class that either creates or maintains an index. Its constructor accepts boolean that can determine whether a new index is created or whether the existing index is open. Document deletion. Lucene provides an index read abstract class that contains methods for deleting documents from an index. Lucene internally refers to document with the document numbers that can change as documents added or deleted from the index. Lucene index optimization. The index optimization is a process to merge all segments to present to an index into a line segment. Optimizing an index is recommended since it improves the search response time. Optimization of index should be done just before closing the index writer. Lucene searching and retrieval. Searching is the process of finding matching document for the input. For the input text. The input text is processed through a chain of analyzers to generate set of terms to be queried. The terms generated from the analysis are used in the query. Lucene search generates a score which is generated using combination of the vector space model VSM of information retrieval and the Boolean model to determine how relevant a given document is to a user's query. Here you can see index in the left side and searching in the right side. Here they are in indexing. It's connected to extract text data, and extract text data is connected to analysis. Analysis is connected to the index tokens, and index tokens are connected to Lucene index. Here the extract text data analysis and index tokens are in indexing here. In searching, pass search string and analysis, and create search Lucene query, search index and Lucene index, and retrieve search result and display results are in searching. And here the pass search string analysis, index tokens, and create Lucene query, search index, Lucene index, and retrieve search index are inside are in Lucene API. Here searching the is connected to a pass search string, and pass search string is connected to analysis. Analysis is connected to create Lucene query. Create Lucene query is connected to search index. Search index is connected to Lucene index. Lucene index is connected to retrieve search result. Retrieve search result is connected to display result and provided the result. Here you can see a basic search application. A lot of application may choose to go for other search integration solutions like Apache Solr, Elasticsearch, which are built on top of Lucene, or just opt in to use NoSQL databases like MongoDB, Cassandra. However, Apache Lucene over its alternative the ecosystem, Java ecosystem integration. If your project is built using Java or integrates well with Java, Lucene's integration within the Java ecosystem can be an advantage to granular control. Lucene allows you to control various aspects of indexing and searching, making it suitable for complex use cases. Indexing and searching performance. Lucene, being a low-level solution, is known for its indexing and searching performance, making it a solid choice for projects that require efficient search operations. Ranking control. For ranking control, Lucene provides a high level of control over ranking of search results and what should be shown to other users. If an application faces this requirement, you may opt to go to Apache Lucene as their search solution. In fact, for those of you who want Samsung phone, the search on your device is powered by Lucene. The two main steps involved in search application which Lucene library provides support for are indexing. First one, indexing the document in searchable format. Two, passing the search query and returning the relevant result. Indexing to search large amount of text quickly, you must first index the text and convert it to a format that will let you search in rapidly, eliminating the slow sequential scanning process. This conversion process is called indexing. And its output is called an index. Most such applications use inverted index. The inverted index is designed to facilitate efficient keyword-based searches by storing the mapping of the terms to the document where they apply. The core Lucene classes for indexing. Document. The document class is a Lucene context, refers to the searchable object we want to search for in our search application. Document is a container for various fields. The field class represents the specific attribute or piece of information associated with the document which we want to index and make searchable. It consists of a key value pair, field name, and the content we want to index. Index writer. The index writer class acts as a component which create and update indexes during the indexing process. Analyzer. The analyzer class is responsible to analyze the document and get the tokens and words from the text which is to be indexed. Directory. The directory class represents the storage location of the indexes on your disk. Searching with Lucene. When you search in Lucene, you formulate queries that target specific field or combination of combination of fields, Lucene inverted index efficiently point to the documents that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching, the index searcher class acts as a core component which read searches index created after the indexing process. The field class is the lowest unit of searching. It is similar to field indexing process. The query class is an abstract class and contain various utility methods and is the parent of all types of queries that Lucene uses during search process. Term query. The term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of it. Top docs point to the top end search result which matches the search criteria. Query parser, the Lucene query parser utility. Query parser is a utility class that allows you to construct queries using user-friendly query syntax. In Apache Lucene, the analyzer is a critical component used for text processing during both indexing and searching. It's responsible for breaking down text into individual terms, tokens, normalizing those terms, and applying optional transformations like stemming or removing stop words. Here you can see the raw content is connected to acquire content. Acquire content is going to build document. Build document is going to do an analyze document. Analyze document is going to index document. Index document is going to index. And here users are connected to search user interface. Search user interface is connected to build query. Build query is connected to run query. Run query is connected to interacts with index. Run query is connected to render result. Render result is connected to search user interface. Here the search user interface, build query, run query, and index and render result, and acquire content, build document, analyze document, index document, and index document in administration between in the level of administration interface and analytic interface. Here you can see a simple searching process. With the searching with Lucene, when you search in Lucene, you formulate queries that target the specific field or combination of fields. Lucene inverted index efficiently point to the document that match your query terms, allowing for fast retrieval of relevant documents. The core Lucene classes for searching is index searcher. The index searcher class acts as a core component which reads and searches index created such indexes created after the indexing process. Field field class is the lowest unit of searching. It is similar to field in indexing process. Query the query class is an abstract class that contains various utility methods and is the parent of all types of queries that Lucene uses during searching process. Term query. The term query class is the most commonly used query object and is the foundation of many complex queries that Lucene can make use of. Top docs point to the top end search results which matches the search criteria. Query parser, the Lucene query parser is the utility that allows you to construct queries using user-friendly syntax. Here the class analyzer. The analyzer builds token streams in the package analysis that and the analyzer build a token stream which analyze text. It thus represents a policy for extracting index terms from text. Class index searcher implements search over a single index reader. Class index reader an abstract class providing an interface for accessing a point in time view of an index. This is the package Lucene.index. Any changes made in the index via index writer will not be visible until a new index reader is open. It's best to use with directory reader.open index writer to obtain an index reader. If your index writer is in process, when you need to reopen and to see changes in index, it's best to use directory reader.open if change directory reader, since the new reader will share the resources with the previous one when possible. Search of an index is done entirely through this abstract interface, so that the any subclass which implement it is searchable. Class directory in package Lucene.store. A directory provides an abstract layer for storing a list of files. A directory contains only files, no subfolder hierarchy. A class topdocs in Apache.lucene.search represent hits returned by index.searcher .search query int. Here the expression is connected to query parser. Query parser interacts with the analyzer via text fragment, and query parser is connected to index searcher via query object. Index searcher is connected to index reader, and index reader is connected to directory. And here the indexed search is connected to topdocs. Now we are considering VCM score in the TF IDF similarity defines the component of Lucene scoring. Overriding computation of this component is convenient way to alter Lucene scoring, suggesting here we are discussing how Lucene scoring evolves from underlying information retrieval models to efficient implementation. We are considering on VSM score. Lucene combines Boolean model BM of information retrieval with the vector space model VSM of information retrieval. The documents approved by BM are scored by VSM. In VSM documents and queries, documents and queries are represented in weighted vectors in a multidimensional space where each distinct index term is a dimension. The weights are in TF IDF values. VSM does not require weights to be TF IDF values, but TF IDF values are believed to produce search result of high quality, and so Lucene is used TF IDF. TF and IDF are described in more I'm going to describe in more details now, but for now the completion, let's just say that given term T and the document or query X, TF function T comma X varies with the number of occurrence of the term T in X. When one increases, so does the other. and the IDF function, the parameter t, similarly varies with the inverse of the number of index document contained in term t. VCM is score is of document D for query Q is a cosine similarity of the weighted query vectors VQ and VD here, where VQ and VD dot VD is the dot product of weighted vectors, and here the absolute VQ and here the absolute V are the Euclidean norms here, two norms. Note the above here, this equation can be viewed as a dot product of the normalized weighted vectors, in the sense that the dividing VQ by its Euclidean norm is normalizing it to a unit vector. The normalizing normalizing VD to the unit vector is known to be problematic in that it removes all document length information. For some documents, removing this info is probably okay. For example, document made by duplicating certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document contain no duplicated paragraph, this might be wrong. To avoid this problem, a different document length normalization factor is used, which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users here you can see formatting only and the cosine similarity formula here. Now we are considering Lucene conceptual scoring formula. The Lucene refines VSM score for both search quality and usability. Normalizing VD to the unit vector is known to be problematic. That removes all document length information. For some document, removing this info is probably okay. For example, document made by duplicating a certain paragraph 10 times, especially if that paragraph is made of distinct terms. But for the document which contains no duplicated paragraph, this might be wrong. To avoid this problem, different document length normalization factor is used. This which normalizes to a vector equal to or larger than the unit vector doc length norm D. At indexing, users can specify certain document are more important than others by assigning a document boost. For this, the score of each document is also multiplied by its boost value, doc boost D. Lucene is field based, hence each query terms apply to a single field. Document length normalization is by the length of the certain field. In addition to the document boost, there are also document field boost. The same field can be added to a document during the indexing several times, and so the boost of that field is a multiplication of boosts of the separate parts of addition, so part of the field within the document. At such time, users can specify boost to each query, subquery, and each query term. Hence, the contribution of a query term to the score of a document is multiplied by the boost of that query term, query boost Q. The document may match the multi-term query without containing all terms of that query. So this is the correct for some of the queries. Under simplifying assumption of a single field in the index, we get Lucene conceptual scoring formula here. The conceptual formula is a simplification in the sense that one terms and the documents are fielded, and the two boosts are usually per query term rather than per query. Now we describe how Lucene implement this conceptual scoring formula and derive the Lucene's practical scoring function. For efficient score, for efficient score computation, some scoring components are computed and aggregated in advance. Query boost. For the query, actually, for each query term is known when search starts. Query Euclidean norm can be computed when the search starts, and it is independent of the query being scored. From search optimization perspective, it is valid question why bother to normalize the query at all, because all scored documents will be multiplied by the same query Euclidean norm, and hence the documents ranks, they are order by score will not be affected by this normalization. There are two good reasons to keep this normalization. Recall the cosine similarity can be used to find how similar two documents are. One can use Lucene for example, clustering, and use a document as a query to compute its similarity to other documents. In this use case, it is important that the score document D2, D3 for query D1 is comparable to the score of document D3 for query D2. In other words, the score of document two distinct queries should be comparable. There are other applications that may require this, and this is exactly what normalizing the query vector VQ provides. Comparability to a certain context extent of two or more queries. Document length norm, doc length norm D, and the document boost, doc boost D, are known at indexing time. They are computed in advance, and their multiplication is saved as a single value in the index. Norm D, index norm D, in the equations in the index norm D. Here you can see a Lucene conceptual scoring formula. Now we are considering Lucene practical scoring function. The document length norm, doc length norm, and the document boost, doc boost D, are known for at indexing time. They are computed in advance, and their multiplication is saved as a single value in the index norm D. Sorry, norm D is not here. In the equations here, the norm T in D means norm field T in doc D, where field T is the field associated with the term T. Lucene's practical scoring function is derived. The color codes demonstrate how it relates to those of the conceptual formula, where TF T in D correlates to terms frequency, defined as a number of times terms T appeared in the currently scored document. Documents that have more occurrences of a given term received a higher score. Note that TF T in Q is assumed to be 1, and therefore it does not appear in this equation. However, if the query contains twice the same term, there will be two term queries with that same term, hence the computation would still be correct, although not very efficient. The default computation for TF T in D in classic similarity is term frequency computation. TF T in D equal frequency to the power half. IDF T stands for inverse document frequency. This value correlates to the inverse of doc freq, the number of documents in which the T time T appears. This means rarer terms gives higher contribution to the total score. IDF T appears in T both in the query and the document. Hence it is squared in the equation. The default computation for IDF T in classic similarity is IDF T equal 1 plus log inverse document frequency computation doc min plus 1 divided by doc freq plus 1. Sorry, doc 1 plus log as parameters function arguments as doc. Sorry, 1 plus doc open curly brace doc count plus divided by doc freq plus 1 close curly brace. T dot get boost is a search time boost of term T in the query queue as specified in the query text, or as set by wrapping the query boost with boost query. Notice that there is really no direct API for accessing a boost of one term in multi-term query, but rather multi-terms are represented in a query as multi-term query object, and so the boost of a term is query is accessible by calling subquery getBoost method. Norm TD is an index time boost factor that slowly depends on the number of tokens of the field in the document, so that shorter field contribute more to the score. So here you can see the Lucene conceptual scoring formula. Here you can see a scorer in a search. Scorer is a core of the search process in Lucene. Scorer is responsible for identifying matches and scoring hits from set of documents present. Scorer is a special class. It is also an extension of a class known as doc ID set iterator. Doc ID set iterator allows iteration over document IDs, thus allowing seek over the index to get a specific document or to iterate over all documents. Note that the iterator can go forward only, it cannot go backward. This restriction simplifies the underlying codex supporting the iterator. Doc ID set iterator provides three useful methods. Doc ID method get the internal index document ID for this document. This method always returns monotonically increasing document IDs. Next doc method iterate to the next doc and advance to the location specified. This interface allows the scorer to iterate over all documents and determine whether they are relevant to the query. The scorer works by implementing scorer method on top of iterations. The score method gets the current document ID and gets the current document and returns the score for the same. The index reader has statistic about the current document that can be fully utilized by the scorer to determine the score. If terms vectors are enabled for the field, the scorer can get access the index reader is here. The index reader has statistic about current document that can be fully utilized by the scorer to determine the score. If the term vectors are enabled for the field, and the scorer get access to the term vector and perform even more elaborate operations. How scoring is performed, here you will see how it all fit together. The user issues a query with the instance of a query class. Query is given by a given to an index searcher, which first rewrite the query recursively, invoking any modification or simplification is possible. Upon completion of the rewrite, the instance of the wait class is created, which is specific to the query plus index searcher combination. This wait will contain all the query specific statistics that apply to the execution of this query. During the scoring, the wait creates a score which iterates over all documents in the index, filters out the irrelevant document, and applied the scoring algorithm on the candidate documents. The scoring algorithm can be anything that the user chooses to implement or use, but typically is a version of terms, frequency, inverse document, frequency, TF, IDF family. Score interacts with the index reader to get relevant details from the underlying file directory. If a term vector is present, the scorer can choose to use features from that as well as calculate scorer for the document. Scorer is expected to return a score per document it iterates on. After scoring completes, the results are returned to a collector, which then chooses the next set of steps. If the top n hits are requested, the collector typically will remain in a priority queue to identify top n hits and then return them back to the user. Here the class query in package org.apache.lucene.search, abstract base class for queries. Class index searcher implements search over a single index reader. Class weight, the expert the calculate query weights and build query scorers. Class scorer, expert common scoring functionality for different types of queries. A scorer exposes an iterator method over documents matching a query in increasing order of the doc ID. Class index reader in package org.apache.lucene.index. Index reader is an abstract class providing an interface for accessing a point-in-time view of an index. Interface collector in org.apache.lucene.search. Expert, the collectors are primarily meant to be used to gather raw results from search and implement scoring or custom filtering, collation, etc. Lucene score collectors are derived from the collector and simple collector. Here the you can see the query. Then query is connected to search index searcher. Index search is connected to wait. Wait is connected to score. Score interacts with index reader, and score is connected to collector. As an example, we can consider org.apache.lucene.search package code to search indices. As an example too, we can consider this code segment. Here the index searcher, class index searcher, implements search over a single index reader. And here you can see the method public top docs search query int n finds the top n hits find the top n hits for query, and this index search is in package org.apache.lucene.search. Here the field score docs the top hits for the query. Here the score docs here the class store docs holds one hit in top docs. Here the query the abstract base class for queries. In this code you can see this now search the index here and here pass a simple query that searches for text. We can consider this code segment for example 3 and here you can see the class query, the abstract class base class for queries, and this class is in package org.apache.lucene.search. Here you can see term query, a query the class term query here, a query that matches documents containing a term. This may be combined with other terms with a Boolean query. Here with this constructor, this constructs a query for the term here. Here you can see trace query. A query that matches documents containing a particular sequence of terms here. A trace query is built by a query parser for input like New York. Here is this constructor an empty trace query, and the here with the add set term to end of the query trace, and this example is valid for Lucene 4.7.0. If you are using, for example, Lucene 9, you have to replace this code segment with trace query.builder. Here you can see a Boolean query, a query that matches the document matching Boolean combination of other queries. Here this constructor construct an empty Boolean query with here the adds a clause to a Boolean query. Here the enum boolean clause dot occur. Here occur must use this operator to close for clauses that must appear in the matching document, and in here should use this operator for clauses that should appear in the matching documents, and must not use this operator for clauses that must not appear in the matching documents. This again, this code is valid for Lucene 4.7.0. If you are using Lucene, for example 9, replace this code segment with boolean query.builder. Here in this code we can consider integrating field values into the score. This query matches the same document as original query, and computes the scores as similarity plus 0.7 multiplied by feature score. Here the boolean query, a query that matches documents matching boolean combinations of other queries. For example, term queries, price queries, or other boolean queries. Here the class builder, boolean query.builder, a builder for boolean queries. The constructor is a solve constructor. Here with the add method, add a new clause to this boolean query.builder. Here you can see the enum boolean clause.occur. Here the enum constant should use this operator for clauses that should appear in the matching documents. Here the term query, a query that matches the documents containing the term. This may be combined with other terms with the boolean query. The construct boolean query construct term query term. Here construct a query for the term here. Here the method build creates a new boolean query based on the parameters that have been set in this builder. Here you can see a feature field. This is a field that can be used to store static scoring factors into documents here. Here the new saturation query, this returns a new query that will score document as weight as one float, and a reasonably good default pivot value is computed based on index statistics and is approximately equal to the geometric mean of all values that exist in the index here. This is field name and this is feature name. These are belongs to these are in a different package. Actually, it's in Lucene document. Here you can see the class boost query. A query wrapper that allows to give a boost to the wrapped query. Boost values that are less than 1 will give less importance to this query compared to other ones, while values that are greater than 1 will give a more importance to the scores returned by this query. Here you can see the constructor wrap query in such a way that the produced scores will be boosted by here the boost. This is the query and this is the boost. And here you can see the query builder, boolean query dot builder. Here is add and the build is there. While similarities help score a document relatively to a query, it is also common for documents to hold features that measure the quality of a match. Such features are best integrated into the score by indexing a feature field with the document at index time. And then combining the similarity score and the feature score using a linear combination. Here the query matches the same document as original query and computes scores as similarity score plus 0.7 multiplied by feature score. In this example, you can see integrating field values into a score. In this example, shows how to compute scores as similarity score multiplied by math.block popularity using expressions module. And assuming that values for the popularity field have been set in numeric in a numeric doc values field at the index time. Here the sort field stores information about how to sort documents by terms in an individual field. Fields must be indexed in order to sort by them. Here in the constructor creates a sort by terms in a given field with the type of return type of term values explicitly given. Here short field dot type dot score, and here you can see int, and here you can see compile an expression. Here you can see symbol bindings just maps variables to short field instances. Here create a query that matches based on the original query but scores using expression. The less efficient yet more flexible way of modifying scores is to index scoring features into doc value fields and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute scores as similarity score multiplied by math.log popularity using expressions module and assuming that values for the popularity field have been set to a numeric doc values field at the index time. As an now we are considering search basics in package octopus.lucene.search. To perform a search, application usually called index.search query int. The public top docs search query int n find the top n hits for a query. This is in the class index searcher implements search over a single index reader, and in the package octopus.lucene.search. Lucene offers a wide variety of query implementations, most of which are in this in the package of apache.lucene.search or the queries module. These implementations can be combined in a wide variety of ways to provide complex querying capabilities along with the information about where the matches took place in the document collection. The query class section highlights some of the more important query classes. To perform a search, applications usually call index.reader.search query int. Once query has been created and submitted to an index searcher, the scoring process begins. After some infrastructure setup, the control finally passes to the weight implementation and its scorer or bulk scorer instances. Now we are considering term query in query classes. Constructing a term query is as simple as this, and the class term query in package octopus.lucene.search a query that matches document containing a term. This may be combined with other terms with the Boolean query. Of the various implementation of query, the term query is the easiest to understand and the most often used in applications. The term query matches all the documents that contain specific term, which is a word that occurs in a certain field. Thus, the term code identifies and scores all documents that have the field with the specified string in it. Constructing a term query is as simple as this. In this example, the query identifies all documents that have the field named field name and containing the word term. There are other query classes: Boolean query, point range query, fuzzy query. Now we are considering scoring. The introduction in scoring. Lucene scoring supports a number of pluggable information retrieval models, including these. Lucene scoring is a heart of why we all love Lucene. It's blazingly fast and it hides almost all of the complexity from the user. In a nutshell, it works. At least that is until it doesn't work or doesn't work as one would expect it to work. Then we are left digging into Lucene internals and asking for help in java-user at lucene.apache.org to figure out why the document of five of our query terms score lower than the different document with only one of the query terms. While this document won't answer your specific scoring issues, it will hopefully point you to the places that can help you figure out what and why Lucene is scoring. You can contact the for the help java-user at lucene.apache.org. Lucene scoring supports a number of pluggable information retrieval models, including vector space model, VSM, probabilistic models such as Okapi, BM25 and DFR, language models. These models can be plugged in via Similarity API and offer extension hooks and parameters for running. In general, Lucene first finds the document that need to be scored based on the Boolean logic in the query specification, and then rank this subset of matching documents via retrieval model. For some valuable references on VSM and IR, in general refer to the Lucene wiki IR references. Now we are considering scoring basics. To be sure to use the useful index searcher.explain query doc to understand how the score for a certain matching document was computed. The method public explanation explain query int doc returns an explanation that describes how doc scored against query in class index is in the class index reader in the package org.apache.lucene.search. The scoring is very much dependent on the way documents are indexed. So it is important to understand indexing. Be sure to use the useful index searcher.explain query.doc to understand how the score for a certain matching document was computed. Generally, the query determines which documents match a binary decision, while similarity determines how to assign scores matching documents. Now we are considering integrating field values into a score in changing scoring in similarity. For instance, this query matches the same document as original query and computes the score matches the same this query matches the same document as original query, and computes scores as similarity score plus 0.7 multiplied by feature score. While the class query in package.apache.lucene.search, the abstract class for queries here. While similarities helped score a document relatively to a query, it also command for a document hold features that measure the quality of a match. Such features are best integrated into the score by indexing feature field with the document at index time, and then combine the similarity score and the feature score using linear combination. For instance, this query matches the same document as original query. And compute the score similarity score plus 0.7 multiplied by feature score. The less efficient yet more flexible way of modifying scorers is to index scoring features into doc value fields, and then combine them with the similarity score, and then combine them with the similarity score using function score query. From the queries module. For instance, this example shows how to compute score as similarity score multiplied by with the similarity scoring using the function score query from the module queries module. For instance, this example shows how to compute scores as similarity score multiplied by math.log popularity using expressions module. And assuming that values for the popularity field have been set in numeric doc values field at index time. Compile an expression. Simple bindings just maps variables to score field. Variables to short field instances. Create a query that matches based on the original query but scores using EXPR. Now we are considering custom queries expert level. The query class in custom queries expert level, the query class has several methods that are important for derived classes. The class query in package Lucene.search, the abstract class for queries. In some sense, the query class is where all it begins. Without a query, there would be nothing to score. Furthermore, the query class is the catalyst for other scoring classes, as it is often responsible for creating them or coordinating the functionality between them. The query class has several methods that are important for derived classes. One, create weight, index searcher, score mode, float boost. A weight is the internal representation of the query, so each query implementation must provide an implementation of weight. The rewrite index searcher method, the rewrite queries into primitive queries. Primitive queries are term query, boolean query, and other queries that implement create weight, index searcher, score mode, float boost. Now we are considering search algorithm. In search algorithm, these important objects are involved in the search. The class index searcher in package Lucene.search implements search over a single index reader. This section is mostly notes. Now we are mostly notes on the stepping through a scoring process and so as well as for the earlier sections. In the typical search application, queries pass to an index reader beginning the scoring process. One side of this, inside the index searcher is a collector is used for scoring and sorting of the search results. The important object involved in a search. One, the weight object of the query. The weight object is internal representation of the query that allows the query to be reused by index searcher to the index searcher that initiated the call. 3, the sort object for specifying how to sort the result if the standard score based method is not desired. Assuming we are not sorting, since sorting doesn't affect the raw Lucene score, we call one of the search method of the index searcher passing in the weight object created by index searcher.create weight query score mod float and the number of results we want. This method returns top doc's object which is an internal collection of the search results. Index searcher creates the top score doc collector and passes it along with the weight to another expert search method. For more on the collector mechanism, see index searcher. The top scorer doc collector uses priority queue to collect the top result for the search. At least we are actually going to score some documents. The score method takes in the collector, most likely the top score doc collector or top field collector, and does it business. Of course, here is where things get involved. Scorer that is returned by the weight object depends on what type of query has submitted. In the most real world application with multiple query terms, the scorer is going to be Boolean scorer to created from the boolean weight. Assuming boolean scorer 2, we get an internal scorer based on the required optional prohibited part of the query. Using this internal scorer, the boolean scorer 2, then proceed into the while loop based on docIterator.nextDoc method. The nextDoc method advances to the next document matching the query. This is an abstract method in the scorer class and is thus overridden by all derived implementation. If you have a simple or simple O query, your internal scorer is most likely a disjunction sum scorer, which essentially combines the scorers from the sub scorers of the odd terms. Now we are considering class expression. The example that shorts based on an expression. The Lucene 9.7.0 expression API. The expression module is the new to Lucene 4.6. It provides an API for dynamically computing per document values based on the string expressions. The class expression in package ogla.lucene.expressions, base class that computes the value of an expression for a document. Example that short based on an expression. Here the example that modify the scores produced by the query. Here the compile an expression. Here the simple bindings just maps variables to short field instances. Here the create short field and sort by it reverse order. Here the compile an expression. Simple binding just maps variables to the short field instances. Create a query that matches based on the body colon contents, but scores using exp expression here. Here we are considering Lucene 9.7.0 facet API, provides facet indexing and search capabilities. Now we are considering Lucene, the package, the package org.apache.lucene.search.grouping in Lucene 9.7.0 grouping API. A typical use for a generic two-pass search grouping search look like this using the grouping convenience utility, optionally using caching for second pass search. The class group search in package org.apache.lucene.search.grouping convenience class to perform grouping in a non-distributed environment. A typical usage for a generic two-pass grouping search look like this using grouping convenience utility, optionally using caching for second pass search. With regarding package org.apache.lucene.search grouping, the grouping this module enables search result grouping with Lucene, where it's the same value in the specified single value group field are grouped together. For example, if you group by an author field, then all documents with the same value of the author fall into the single group. Grouping requires a number of inputs. Group selector, this define how groups are created from values per document. Grouping module ships with selectors for grouping by term or by long or double ranges. Group sort, how the groups are sorted. For you grouping sorting process, each group is represented by the highest sorted document according to the group sort within it. For example, if it's price ascending, then the first group is the one of the lowest price booked within it. Or if you specify relevant group short, then the first group is the one containing highest scoring book. Top n groups, how many top groups to keep. For example, 10 means the top 10 groups are compiled. Group offset, which slice of top groups you want to retrieve. For example, 10 means the top 10 groups are computed. Group offset, which slice of the groups you want to retrieve. For example, 3 means you will get 7 groups back, assuming top n groups is 10. This is useful for paging, where you might show 5 groups per page. Within group sort, how the documents within each groups are sorted. This can be different from the group sort. Max docs per group. How many top documents within each group to keep. Within group offset, which slice of top documents you want to retrieve from each group. The implementation is two pass. First pass grouping collector gathers top groups, and the second pass grouping collector gathers document within these groups. If the search is costly to run, may you want to use caching collector class. Which caches it hits and can quickly replay them for second pass. This way you only run the query once, but you pay a RAM cost to briefly hold all hits. Results are written as top groups. This is within group sort. Groups are defined by group selector implementation. Term group selector groups based on the value of the shorted doc fields. Value source group selector groups based on the value of value source. Double range group selector groups based on the value of a double value source. Long range group selector groups based on the value of a long value source. The known limitation: sharding is not directly supported, though it is not too difficult if you can merge top groups and the top documents per group yourself. Typical usage for generic two-pass grouping search look like using grouping convenience utility, optionally caching for the second pass search. To use the single pass block grouping collector, first at indexing time you must ensure all the docs in a groups are added as a block. And you have some way to find last document of each group. One simple way to do is to add marker binary field. Then and then at the search time here, or alternatively use group search convenience utility. Another collector is all groups head collector that can be used to retrieve all most relevant documents per group. Set cache in MB. Require total group count. Render grouped result. Create documents from your source. You can also use the writer.update document. Just be sure you replace then an entire previous doc block with this new one. For example, each group could have a group ID field with the same value for all docs in this group. Render group result. Now we are considering Lucene 9.7.0 highlight API. The package org.apache.lucene.search.highlight here, highlight in the API. This is an example usage. The class highlighter in package org.apache.lucene.search.highlight marks and highlighted terms found in the best sections of text using configurable fragmenter, scorer, formatter, encoder, tokenizers. The highlight package contains classes to provide keyword in context features typically used in highlight search terms in the text result pages. The highlighter class is a central component that can be used to extract most interesting sections of a piece of text and highlighting them with the help of fragmentator, fragment score, and formatter classes. Here is an example usage. Above create the documents with two fields, one with the term vectors TV and one without no TV. Term vector. Now we are considering package org.apache.lucene.monitor in Lucene 9.7.0 monitor API. A number of method types are included. The class monitor in package org.apache.lucene.monitor. A monitor contains a set of query objects with associated IDs, and efficiently matches them against set of document objects. A number of matches types included here. The and the in the package Lucene.monitor, the monitoring framework, this package contains classes to allow monitoring of a stream of document with a set of queries. Here a number of matcher types are included. Query match.simple matcher just returns the set of query IDs that a document has matched. Scoring match with similarity Lucene.search.similarity returns a set of matching queries with the scores that each one records against document. Similar to scoring match but include full explanation, returns the matching queries along with the matching terms of each query. Matches can be wrapped in partition matcher or parallel matcher to increase performance in low currency systems. Now we are considering Lucene the Lucene 9.7.0 Spatial Extras API, the Spatial Extras module for Apache Lucene. The Spatial Extras module uses Spatial 4J heavily. Spatial 4J is an ASL license library with these capabilities here. The class Spatial strategy in package Apache.lucene.spatial. The Spatial strategy encapsulates an approach to indexing and searching based on shapes. The Spatial Extras module new to Lucene for 6.5 is new home for original Lucene Spatial module. The principal interface is this module is Spatial strategy, which can calculate approach to indexing and searching based on shapes. Different strategies have different features and performance profiles, which are documented at each strategy's implementation class level. For some sample code, the Spatial Extras module uses Spatial 4J heavily. The Spatial 4J is an ASL license library with these capabilities. Provides shape implementation, namely point, rectangle, and circle. Both geospatial context and plain 2D Euclidean Cartesian contexts are supported. With additional dependency, it adds polygon and other geometry shape supports via integration with JTS topology suite. This include dateline wrap support. Shape parsing and serialization, including well-known text WKT via JTS, distance and other spatial-related math calculations. Historical note: the Spatial Extras module was once known as Lucene Spatial Playground (LSP) as an external project. In March 2012, the LSP split into Spatial module as part of the Lucene and Spatial 4J externally. A large chunk of LSP implementation originated as LR2155, which uses tri-prefix tree algorithms with geohash encoding. That approach is implemented in recursive prefix tree strategy today. An example, we can consider class index searcher dot too many clauses thrown when an attempt is made to add more than get max clause count clauses. This typically happens if a prefix query, fuzzy query, wildcard query, or term range query is expanded to many terms during search. This is in package org.apache.lucene.search. As an error example, we can consider this error o.e.b. Elasticsearch uncaught exception handler. Fatal error occurred in thread existing and etc. And here at org.apache.lucene.search.search.index.search.searcher.search indexsearcher.java 665 etc. This is occurred in the environment with Elastic Stack and Elasticsearch. Now we are focusing on search result. Here you can see a look. You can also perform some searches in the search tab. Look is the tool of choice to understand search results. It is a free Java utility that lets you analyze a Lucene index. You can perform some searches here in the search tab here. The search works using a series of one or more field name colon term predicates. For example, you can think of this one here, title colon hello, here content type dot telnik. Note that the query is case sensitive. The field name should always use the exact same case here than the field name displayed, but the term should always be lowercase here. For adding a plus before predicate, here indicates it is mandatory. If you put plus here, searches for the content whose title contains both here content type and telnik. Here notice how the content type field indicates the type of the content you are dealing with here. When the result shows up when it shouldn't, it is generally because site infinity here is indexing a similar term of another type. The content type combined with the ID and sometimes the link field helps pinpoint the exact item being indexed. As an example, we can consider this one here. The class scoredoc holds one hit in top docs. And here you can see this is asset equals 1 with the length, and iterate through the result here. And this is asset equal, this is the text to be indexed here. And here the score docs are in package og.apache.lucene.search. So here we are asserting the search result. As an error example, we can consider total hits cannot be converted to long. Now we are focusing on files to be indexed. A computer file is a computer resource for recording data in a computer storage device, primarily identified by its file name. Just as words can be written to a paper, so can data be written to a computer files. Files can be shared with and transferred between computers and mobile devices via removable media networks or the internet. Search engine indexing is the collecting, parsing, and storing of data to facilitate fast and accurate information retrieval. Index design incorporates interdisciplinary concepts from linguistics, cognitive psychology, mathematics, informatics, and computer science. An alternative name for the process in the context of search engine designed to find web pages on the internet is web indexing. Here we are considering adding a file to the index class file, an abstract representation of file and directory path names. This is in package java.io. The once we created the index directory, let's go ahead and add a file to the index. Here we create document with two string fields named path and file name, and a text field called contents. Note that we pass the file reader instance as the second parameter to the text field. The document is added to the index using index writer. The third argument in the text field or string field constructor indicate whether the value of the field will also be stored. Finally, we invoke the close method of the index writer to gracefully close and release the lock from the index files. Here we are considering index as a single document. Here interface path, an object that may be used to locate a file in a file system, will typically represent a system dependent file path. This is in package java.nio.file. This is here the make a new empty document. Here add the path of the file named path, use a field that is indexed, that is searchable, but don't tokenize the field into separate words and don't index term, frequency or positional information. Here at the last modified date of the file, a field name modified, use long point that is indexed, that is efficiently filterable with point range query. This indices to multi-second resolution, which is often too fine. You could instead create a number based on year, month, day, hour, minutes, seconds down the resolution you require. For example, long value 2011 021714 would mean February 17th 2011 2 to 3 p.m. Add the content of the file to the field name contents. Specify a reader so that the text of the file is tokenized and indexed but not stored. Note that the file reader expect the file to be UTF-8 encoding. If that's not the case, searching for special characters will fail. And the new index, so we just add the document no all document can be there, and adding file, and here this is the index writer. So if the existing index and all copy of this document may have been indexed, so we use update document instead to replace old one matching the exact path if it represent. Now we are focusing on Lucene analysis language analyzer. org.apache.lucene.analysis defines an abstract analyzer API for converting text from a reader into a token stream and enumeration of token attributes. A token stream can be composed by applying token filters to the output of the tokenizer. Tokenizers and token filters are strung together and applied with an analyzer. Analysis common provide a number of analyzer implementation, including stop analyzer and grammar-based standard analyzer. Here you can see analysis process during indexing. Fields 1 and 2 are analyzed, producing a sequence of tokens. Field 3 is unanalyzed, causing an entire value to be indexed as a single token. Here document has field 1, field 2, field 3, and field 1 is connected to analyze, field 2 is connected to analyze, analyze is connected to update index. Tokens are passed from analyze to update index, and field 3 is connected to update index, and update index is connected to indexed. Here you can see a token stream with the positional and offset information. A stream of tokens are fundamental output of analysis process. During indexing, fields designated for analysis are processed with the specified analyzer, and the important attributes from each token are then written to the index. For example, let analyze the text quit the quick brown fox. Each token represents an individual word of that text. A token carries with it a text value, the word itself, as well as some metadata, start and end of the character, and character offsets in the original text, a token type, a positional increment. The token may optionally be contain application defined bit flags and arbitrary byte array payload, and can easily extend to include any application specific attribute. This figure shows details of a token stream analyzing this phrase with a simple analyzer. The start offset is the character position in the original text where the token text begins, and the end offset is the position just after the last character of the token text. These offsets are useful for highlighting matched token in search results. The token type is a string defaulting to word that you can control and use the token filtering process if desired. As text is tokenized, the position relative to the previous token is recorded as the position increment value. Most of built-in tokenizers leave the position increment value at the default value of 1, indicating that all tokens are in successive positions, one after other. Each token has optional flags. A flag is a set of 32 bits stored in an int that's unused by Lucene's built-in analyzers but could be used by your application. Likewise, each token can have a byte array recorded in the index referred to as payload. Tokens into terms. After text is analyzed during indexing, each token is posted to the index as a term. The position increment start and end offsets and payloads are only additional metadata associated with the token that's recorded in the index. The token type and flags are discarded. They are only used during analysis process. Positional increments. The token position increment value relates to the current token's position to the previous token's position. Position increment is usually 1, indicating that each word is in a unique and successive position in the field. Position increments factor directly into performing praise queries and spam queries, which rely on knowing how far terms are from one another within the field. Position increments greater than 1 allow for gaps and can be used to indicate where words have been removed. A token with 0 position increment places the token in the same position as the previous token. Analyzers that inject synonyms can use a position increment 0 for synonyms. The effect is that praise queries work regardless of which synonym was used in the query. Here you can see the quick brown fox here, and you can see the offsets here, and positional increments are here. Here you can see a standard analysis pipeline. The Lucene analysis Java doc provides a good overview of the moving parts in the text analysis pipeline. At a high level, you can think of the analysis pipeline as consuming a raw stream of characters at the start and producing terms roughly corresponding to words at the end. The standard analysis pipeline can be visualized as such here. We will see how here you can see the input stream, standard tokenizer, lowercase filter, and stop word filter here. Here the Lucene is easy, Steve told us. Here the standard tokenizer, Lucene is easy, Steve. Here in this case, then input stream is connected to standard tokenizer. Standard tokenizer is connected to lowercase filter. Here Lucene is easy, Steve, lowercase L and S, and lowercase filter is connected to stop word filter. Here the Lucene easy, Steve told. Here you can see the workflow of the new token stream API as follows here. One instantiation of token stream, token filters which add or get attributes to or from the attribute source, to consume the consumer call reset, 3. Consumer retrieves attributes from the stream and store the local references to all attributes it wants to access. 4. The consumer calls increment token method until it returns false, consuming the attributes after each call. 5. The consumer calls end method so that any end of stream operations can be performed. 6. The consumer calls close method to release any resource when finished using the token stream. To make sure that the filters and consumers know which attributes are available, the attributes must be added during instantiation. Filters and consumers are not required to check for availability of attributes in increment token method. You can find some example code for new API in analysis package level Java doc. Sometimes it is desirable to capture the current state of a token, for example the buffering process. For this use case, buffering process, the token stream API in Lucene is based on the decorator pattern. Therefore, all non-abstract subclasses must be final and have at least a final implementation of increment token method. This is checked when Java assertions are enabled. An example, we can consider this code segment. Here the class analyzer. An analyzer builds a token stream which analyzes text. It does represent a policy for extracting index terms from text. Here the standard analyzer filters standard tokenizer with standard filter, lowercase filter and stop filter using a list of English stop words. This class analyzer here is in package org.apache.lucene.analysis. As an example too, we can consider this code segment here. When you are invoking an analyzer, application usually do not invoke analysis. Lucene does it for them. Applications construct analyzers and pass them into Lucene as follows. At indexing as a consequences of add document doc, the analyzer in effect for indexing is invoked. For each index field is added to the document. At search, a query parser may invoke analyzer during parsing. Note that for some queries, analysis does not take place. For example, wildcard queries. However, an application might invoke analysis of any text for testing or for any other purpose, something like this. Here you can substitute desired Lucene version for X and Y here. Here standard analyzer or any other analyzer. The analyzer class will construct the tokenizer, token filters and char filters and pass the resulting readers to the tokenizer. Here reset this stream to the beginning required. Here they use attribute source dot reflect as string boolean for token stream debugging. Here perform end of stream operations, that is set the final offset, and finally release resources associated with this stream. An analyzer builds a token stream which analyzes text. It thus represents a policy for extracting index terms from text. In order to define what analysis is done, subclasses must define their token stream components. In create components string, the components are then used in each call for token stream string reader. Here is a sample simple example. Here create a new analyzer token string components instance for this analyzer, and here in the normalize wrap the given token stream in order to apply normalization filters. Assuming foo filter is about normalization and bar filter is about stemming, only foo filter should be applied. So adding a length filter, here the class filtering token filter, abstract base class for token filters that may remove tokens. You have to implement a accept method and return a boolean if the current token should be preserved. Increment token method uses this method to decide if a token should be passed to the caller. This is in package org.apache.lucene.analysis. Here in the length filter, the char term attribute is added and stored in the instance variable. Remember that there can only be a single instance of char term attribute in the chain. So in this example, the add attribute call in the length filter returns the char term attribute that the white space tokenize already added. In the tokens are retrieved from the input stream in filtering tokens filters increment token method, which calls length filters accept method. That is not shown here. And by looking at the term text in the char term attributes, the length of the turn can be determined. and tokens that are either too short or too long are skipped. Note how accept can efficiently access the instance variable, and no attribute lookups is necessary. The same is true for the consumer, which simply use local references to the attributes. As example 6, we can consider this one, hibernate.search.analyzer equal org.apache.lucene.analysis.es.spanish analyzer. This is configuring an analyzer in OpenKM. For that, edit the $tomcat_home/openkm.configure cfj file and add this line here. And now here as an example, we are considering package org.apache.lucene.analysis text analysis API and code to convert text into indexable or searchable tokens, covers, analyze, and reader classes. Now we are considering parsing, tokenization, analysis in package org.apache.lucene.analysis. Lucene and indexing and search library accept only plain text input. Now we are considering parsing. Applications that build their search capabilities upon Lucene may support documents in various formats: HTML, XML, PDF, Word, just to name a few. Lucene does not care about the parsing of these and other document formats, and it is the responsibility of the application using Lucene to use the appropriate parser to convert the original format into the plain text before passing that plain text to Lucene. Now we are considering tokenization. There are many post-tokenization steps that can be done, including but not limited to plain text passed to the to Lucene for indexing goes through a process generally called tokenization. Tokenization is the process of breaking input text into small indexing element tokens. The way input text is broken into tokens heavily influences how people will then be able to search for that text. For instance, sentences beginning and ending can be identified to provide more accurate praise and proximity searches, though sentence identification is not provided by Lucene. In some cases, simply breaking the input text into tokens is not enough. A deep analysis may be needed. Lucene includes both pre- and post-tokenization analysis facilities. Pre-tokenization analysis can include, but it is not limited to, stripping HTML markup and transforming or removing text, matching arbitrary patterns or sets of fixed strings. There are many post-tokenization steps that can be done, including but not limited to stemming, replacing words with their stems. For instance, if the English stemming bikes is replaced with bike, now query bike can find both documents containing bike and those containing bikes. Stop words filtering. Common words like the and rarely add any value to a search. Removing them shrinks the index size and increases performance. It may also reduce some noise and actually improve search quality. Text normalization. Stripping accent and other character makings can make for better searching. Synonym expansion. Adding a synonym at the same token position as the current word can mean better matching when users search with words in the synonym set. Now we are considering co-analysis. These are here. The class analyzer in package org.apache.lucene.analysis. An analyzer build token streams which analyze text, thus represent a policy for extracting index terms from text. Class char filter in package org.apache.lucene.analysis. Subclasses of char filter can be chained to filter a reader. They can be used as a reader with additional offset correction. Tokenizers will automatically use correct offset int if the char filter subclass is used. Class tokenizer in package of Apache Lucene.analysis. A tokenizer is a token stream whose input is a reader. Class token filter in package of Apache Lucene.analysis. A token filter is a token stream whose input is another token stream. The analysis package provides a mechanism to convert strings and readers into tokens that can be indexed by Lucene. There are 4 main classes in the package from which all analysis processes are derived. These are analyzer. An analyzer is responsible for supplying a token stream which can be consumed by indexing and searching processes. Most of the time you can use an anonymous subclass of analyzer. Char filter extends reader to transform the text before it is tokenized while providing corrected character offsets to account for those modifications. This capability allows highlighting to function over the original text when indexed tokens are created from the char filter modified text with offsets that are not same as those in the original text. Tokenizer.setReader java.io.reader accept char filters. Char filters may be chained to perform multiple pre-tokenization modifiers. Tokenizer. A tokenizer is a token stream and is responsible for breaking up incoming text into tokens. In many cases, an analyzer will use a tokenizer as the first step in the analysis process. However, to modify text prior to tokenization, use a char filter subclass. Token filter. Token filter is a token stream and is responsible for modifying tokens that have been created by the tokenizer. Common modification performed by the token filter are deleting, stemming, synonym injection, and case folding. Not all analyzers require token filters. Now we are considering hints, tips and traps. To ease this confusion, here is some clarifications. The relationships between analyzer and char filters and tokenizers and token filters is sometimes confusing. To ease this confusion, here are some clarifications. The analyzer is a factory for analysis chains. Analyzers don't process text. Analyzers construct char filters, tokenizers, or token filters that process text. An analyzer has 2 tasks: to produce token streams that accept a reader and produces tokens, and to wrap or otherwise pre-process reader objects. Char filter is a subclass of reader that supports offset tracking. The tokenizer is only responsible for breaking the input text into tokens. The token filter modifies the stream of tokens and their contents. Tokenizer is a token stream, but analyzer is not. The analyzer is field aware, but tokenizer is not. Analyzers may take field name into account and when constructing a token stream. If you want to use particular combination of char filters, a tokenizer, and some token filters, the simplest thing is often and create an anonymous subclass of analyzer. Provide analyzer.create component string and perhaps also analyzer.initReader string java.io.reader. However, if you need some same set of component over and over in many places, you can make subclasses of analyzer. In fact, Apache Lucene supplies a large family of analyzers class that deliver useful analysis chains. Most common of these is the standard analyzer. Many applications will have a long and industrious life with nothing more than standard analyzer. The Analyze Common library provides many pre-existing analyzers for various languages. Analysis Common library also allows to configure custom analyzer without subclassing using the custom analyzer class. Aside from the standard analyzer, Lucene includes several components containing analysis components, all under the analysis directory of the distribution. Some of these support particular languages, other integrate external components. The common subdirectory has some noteworthy general purpose analyzers, including per field analyzer wrapper. The most analyzers perform some same operation on all fields. The per field analyzer wrapper can be used to associate a different analyzer with different fields. There's a great deal of functionality in the analysis area. You should study it carefully to find the pieces you need. Analysis is one of the main causes of slow indexing. Simply put, the more you analyze, the slower the indexing in most cases. Perhaps your application would be just fine using simple white space tokenizer combined with a stop filter. The benchmark library can be useful for testing out the speed of the analysis process. Now we are considering invoking an analyzer. However, an application might invoke analysis of any text for testing or any other purpose. Application usually do not invoke analysis. Lucene does it for them. Applications construct analyzers and pass then into Lucene as follows. At indexing, the consequence of at document.doc method, the analyzer effect for indexing is invoked for each index field of the added document. At search, the query parser may invoke analyzer during parsing. Note that for some queries, analysis does not take place. For example, wildcard queries. However, an application might invoke analysis of any text for testing or for any other purpose, something like here. Here the class analyzer in package org.apache.analysis, apache.lucene.analysis, an analyzer built token streams which analyze text. It does present a policy for extracting index term from text. Substitute desired Lucene version for XY or any other analyzer here. Analyzer class will construct the tokenizer token filters and char filters and pass the resulting reader to the tokenizer. Reset this stream to the beginning required. Use attribute source dot reflex as string boolean for token stream debugging. Perform end of the stream operations, for example, set the final offset. Release the resources associated with these streams. Now we are considering indexing analysis versus search analysis. Here are some rules of thumb. Selecting the correct analyzer is crucial for search quality and can also affect indexing and search performance. The correct analyzer for your application will depend on what your input look like and what problems you are trying to solve. Lucene's Java wiki page analysis paralysis provides some data on analyzing your analyzer. Here are some rules of thumb. One, test. Did we say test? 2, beware of too much analysis. It must hurt indexing performance. 3, start with same analyzer for indexing and search. Otherwise, searchers would not find what they are supposed to. 4, in some cases, different analyzer is required for indexing and search. For instance, certain searches require more stop words to be filtered. For example, filters that is more than those that were filtered at indexing. Query expansion by synonyms, acronyms, auto spell correction, etc. This might sometimes require a modified analyzer. Now we are considering field section boundaries in implementing your own analyzer and analysis components. Where decides this behavior can be modified by introducing position in a position gap between consecutive field sections simply by overriding analyzer.getPosition increment gap field name. When document.add field is called and the class standard analyzer in package apache.lucene.analysis.standard filters standard tokenizer with lower case filter and stop filter using configurable list of stop words. Field section boundaries when document.add field is called the multiple times for the same field name, we could say that each such call creates a new section for that field in the document. In fact, a separate call to token stream field reader would take place for each of these so-called sections. However, the default analyzer behavior is to treat all these sections as one large section. This allows price search and proximity search to seamlessly across boundaries between sections. In other words, if a certain field f is added like this, then the price search for end starts would find that document. When desired, this behavior can be modified by introducing a position gap between consecutive field sections simply by overriding analyzer.get position increment gap field name. The substitute desired Lucene version for XY. Now we are considering white space tokenization in example in token stream API. In this example, we will create a white space tokenizer. and use a length filter. In this easy example, a simple white space tokenization is performed. The main loop loop consumes white space tokenization is in main method. Loop consumes a stream and prints the term text of the tokens by accessing the chart term attributes that the white space tokenizer provides. Here is the output. Text to tokenize. Substitute the desired Lucene version for XY. Get the char term attributes from the token stream. Print all tokens until stream is executed. Stream is exhausted. Now we are considering a class token stream. This is an abstract class. Concrete subclasses are here. The class token stream in package obj.apache.lucene.analysis. A token stream enumerates the sequence of tokens either from fields of a document or from query text. A token. This is an abstract class. Concrete subclasses are tokenizer, a token stream whose input is a reader, and token filter, a token stream whose input is another token stream. Token stream extends attribute source, which provides access to all of the token attributes for the token stream. Note that one instance per attribute IMPL is created and reused for every token. This approach reduces the object creation and allows local caching of references of the attribute IMPLs. Now we are considering Lucene 9.7.0 Common API and the analysis for Lucene content in different languages and domains. the class English analyzer in package apache.lucene.analysis.en analyzer for English. Now we are considering Lucene 9.7.0 ICU API. This module exposes functionality from ICU to Apache Lucene. ICU4J is a Java library that enhances Java internationalization supported by improving performance, keeping current with Unicode standard and providing richer APIs. Here you can see the tokenizing multi-language text in as example usage. Here the class ICU tokenizer in package apache.lucene.analysis.icu.segmentation. Class they breaks text into words according to UAX #29 Unicode text segmentation. This will work well in general for most languages. Now we are considering Lucene 9.7.0 Kuromochi API. Kuromochi is an morphological analyzer for Japanese text. The class Japanese analyzer in package apache.lucene.analysis.ja analyzer for Japanese that uses morphological analysis. Now we are considering Lucene 9.7.0 Morphologic API. This package provides dictionary-driven lemmatization, accurate stemming, filter, and analyzer for Polish language driven by the Morphologic library developed by David Weiss and Martin Milswoki. The class Morphologic analyzer in package apache.lucene.analysis.morphologic analyzer using Morphologic library. The Lucene 9.7.0 Nori API. Nori is a morphological analyzer for Korean text. Class Korean analyzer in package org.apache.lucene.analysis.ko analyzer for Korean that uses morphological analysis. Lucene 9. Now we are considering Lucene 9.0.0 Open NLP API. This module exposes functionality from Apache Open NLP to Apache Lucene. The Apache Open NLP library is a machine learning based toolkit for processing of natural language text. Open NLP tokenizer. The class Open NLP tokenizer in package apache.lucene.analysis.openLP run OpenNLP sentence detector and tokenizer. The index of each sentence is stored in sentence attribute. Now we are considering Lucene 9.7.0 phonetic API. Analysis for indexing phonetic signatures for sound alike search. Class phonetic filter in package org.apache.lucene.analysis.phonetic. Create tokens for phonetic matches. Now we are considering Lucene 9.7.0 Smart CN API. Analyze for simplified Chinese which indexes words. The class Smart Chinese analyzer in package org.apache.lucene.analysis.cn.smart. Smart Chinese analyzer is an analyzer for Chinese or mixed Chinese English text. The analyzer uses probabilistic knowledge to find the optimal word segmentation for simplified Chinese text. The text is first broken into sentences, then each sentence is segmented into words. Now we are considering Lucene 9.7.0 Stemple API. Stemple the algorithmic stemmer for Polish language. The class Stemple stemmer in package org.apache.lucene.analysis.stemple. Stemmer class is a convenient facade for other stemmer related classes. The core stemming algorithm and its implementation is taken verbatim from the Egoto project www.egoto.org. An exception example we can consider this one IO exception. This can be occurred in method public standard analyze. This can be occurred in constructor public standard analyzer reader stop words in the class standard analyzer. As an array example, we can consider this one package org.apache.lucene.analysis does not exist. Import org.apache.lucene.analysis.analyzer.